All right, so today we're talking about what are known as net change and accumulation problems. And to look at how we're going to approach these kinds of problems, we're going to go back to the fundamental theorem of calculus that told us that if you took the integral from a to b of this function, f at x dx, this was equal to capital F at b minus capital F at a. The caveat was that f had to be continuous on AB, and the relationship between small letter f and capital letter F was that capital F at x is the antiderivative of small letter x. So what does this actually mean here? I.e., if we take capital F at x, okay, and we do the derivative of it, so capital F at x prime, we will get small letter x. And this is just what we mean by antiderivative here. So we can rewrite our fundamental theorem of calculus as the integral from a to b. Instead of small f at x, I'm just going to put capital F at x primed over dx is, of course, equal to, we'll keep the right-hand side the same, capital F at b minus capital F at a. Now, if we look at what we have here on the right-hand side now, we've got f, capital F, primed at x, okay? If we're taking the derivative of this function, what does a derivative represent? Well, graphically, it represented the slope of the tangent. In terms of a function, it represented the rate of change of something. So this term right here is the rate of change of something. I'll just say the rate of something. And we don't know what that something is. That's going to depend on the particulars of the problem that we're trying to answer. Okay? But it's how that thing is changing with respect to x. Okay? If we look at the right-hand side, capital F at b minus capital F at a, we're taking this something that we're finding the rate of change of, okay? So not the rate of change of it, but the actual value of that something. We're evaluating at 2 points, B and A, and we're taking the difference. So the difference between the values at these 2 points is the net change in our function f at x, as x goes from a to b. Okay? So this is like we evaluate it at the starting point, we evaluate it at the ending point, and we take the difference. Okay? So what the fundamental theorem is telling us here is that if we want to find the net change from point A to point B, we can take the integral of our rate of change over this interval. Okay? Right? And the other thing that is kind of interesting here is that if we're taking the integral of our rate of change here, our answer is not going to depend on sort of the path that is taken along the way. It only depends on what the values are at our two endpoints, A and B. So we can just sort of say here, goes from A to B, doesn't depend on path, okay, only the endpoints. In other words, if we've got our function here, capital F at x, we've got a point here at A, we've got a point over here at B, and we want to find the net change. I mean, it doesn't matter whether this thing goes up and then down and then up and then down and up like that, okay? The net change is only telling us the difference between what is going on at this point here and at this point here. So our net change, okay, is just sort of from there to there. Okay? So all of this, we can put this together into what is called sort of our net change theorem. Okay? And the net change theorem says that if capital F primed at x represents the rate of change of some quantity, capital F at B minus capital F at A is equal to the integral of that rate of change over x, and that represents the net change in the quantity from A to B. So let's sort of look at kind of a little of an example of sort of a specific kind of function that this would apply to. So let's say we've got some sort of particle moving in a straight line, and we've got a position function. And our position functions, we always called them sort of s at t. We did a lot of these kinds of questions when we were starting to talk about derivatives. Okay? We would have a velocity function, which would be v at t, of course, was just s primed at t. So what does our net change theorem tell us about our position function and our velocity function? Well, if we take our velocity function, okay, this thing that represents our rate of change, and we do the integral of the velocity function between two times, t1 and t2, and of course we're integrating over t here, what does this represent? It's going to represent the net change in the position from t1 to t2. In other words, s at t2 minus s at t1. Okay, because s is the, well, it's the antiderivative of our velocity. Okay. So this thing over here on our right-hand side, again, is our net change. And when we're dealing with positions, what special name do we give to the net change in the position between two intervals in time? Yeah, we call this the displacement. And as we said, when we were talking about distance and displacement, displacement doesn't depend on the path taken. It just depends on the locations at our two endpoints. Okay? So if we were doing this in terms of, we could have some sort of velocity function that said that our particle, starts up here and it goes down here and it goes up here and sort of ends up over here. Okay? Our net change theorem, let's fix some times here. T1, let's say it goes to T2. If we're doing the integral of this function, okay, the left-hand side here, if we're thinking about what the integral represents, it represents the area between the curve and the axis, or the area under the curve. So we have sort of these three regions, okay, that we would find the area of. A1, A2, and A3. And what's going on with our velocity function here? Well, this thing starts off, it starts off positive, then our velocity goes negative, okay, then it goes back to being positive again. So it kind of changes direction here. It starts off, if its velocity is positive, it's moving to the, if its velocity is positive, it's moving to the right. When it goes negative, it's moving to the left. And then when it goes positive again, it's moving back to the right. Okay. So if we're doing the displacement in terms of these areas, we have to think about these again as positive areas and negative areas and then positive areas again. So we would do something like A1 minus A2 plus A3, okay? Because these are sort of, and these would work out to be positive and negative, okay? If we want to talk about the total distance traveled, remember the difference between distance and displacement is that the distance doesn't take the direction into account. So the path does matter when we're talking about distance. So it I should say depends on direction. So if we were doing distance, we would want to have the total of all three of these areas. Not the net area, but the total area. So we would want to add sort of the absolute value of all of these things, making sure that all of these were positive. Or if we were doing this using integrals, we would do something like we want the integral from t1 to t2 of the absolute value of our velocity function, okay? Taking into account the fact that our velocity is starting at, has these intervals that are positive and negative. So taking the absolute value would make all of these intervals, would ensure that our velocity function is positive over all of these intervals, okay? So the big thing to remember here is our net change theorem, okay? So that's what we're going to apply in the next couple of examples here, okay? So example 1 here of something we were just talking about. Velocity function for a particle moving on a line is given by v at t equals t squared minus 2t minus 8, and this is valid for the interval t between 1 and 6 seconds. Find the displacement and the distance traveled, okay? What we were just talking about here. So our displacement is just going to be the integral of our velocity function with respect to time over the time interval in question. So from 1 to 6. Okay. This comes from our net change theorem. The net displacement is the net change in our position, so we are integrating our velocity function over our two intervals. So we want the integral from 1 to 6 of our velocity function t squared minus 2t minus 8, and we're integrating this whole thing over t. Okay, so how do we evaluate this integral? Well, obviously we need our antiderivative here, so we can, this is this nice little polynomial here, we can do this term by term. 1/3 t cubed minus t squared minus 8t, and we want to evaluate this from 1 to 6. So let's see, we sub in 6 first, and we get, let's see, 1/3 6 cubed minus 6 squared minus 8 times 6, and then we subtract from it what we get when we sub in 1. That's going to be 1/3 minus 1 minus 8. and we evaluate this whole thing, and we get negative 10/3. Exactly. Okay. So our net displacement here is negative. What does that mean, that the net displacement is negative? Is that even possible? Or have I done something wrong here? What do you think, Daphne? Yeah, it ends up to the left of where it started. Okay, so it is possible for the net displacement to be positive. Now, if this was a distance question, is it possible for the distance traveled to be negative? Hayun's shaking his head. Why not, Hayun? You just can't. Yeah, because it's measured. The way you think about distance is whichever direction you're going, you're considering that distance traveled. It's how far you've gone relative to the ground. So you're considering all of these things to be positive. So let's go ahead here and figure out our distance traveled. Okay, and the way that we make sure that all of these distances are considered in the positive direction is we do the same integral from 1 to 6, but we're going to take the absolute value of our velocity function, like we talked about on the previous page. Now, how do we do this? Seems pretty simple here. Let's think about what our velocity function looks like. It is a parabola. It opens up. We can factor it into, let's see, we've got 4 and 2. We've got 2 has got to be positive and the 4 has got to be negative. So clean that up a little bit here. So it's going to have 2 intercepts at negative 2 and positive 4. So this thing is going to kind of look like this. Okay. We want to do the integral from 1 to 6. And then 6 is way over here. So when we do this integral, we're going to have 2 regions. We're going to have this region here from 1 to 4, and then we're going to have this region over here from 4 to 6. So we're going to break our integral up into those 2 parts. We're going to have the integral from 1 to 4 of t squared minus 2t minus 8 dt. And we're going to add to it the integral from 4 to 6 of t squared minus 2t minus 8. Okay. Now, on this interval here from 1 to 4, our velocity function is negative. So when we do this integral, we should come up with something that is negative. On our interval from 4 to 6, our velocity function is positive, so our integral should result in a positive answer. So it's this first one here that if we do the integral, we'll get a negative. We want to switch that negative over to a positive. So we are going to actually take the absolute value of the integral from 1 to 4 of t squared minus 2t minus 8 dt. And we're going to add to it. We don't have to do anything with this second integral because it's going to work out to be positive already. Minus 8. Sorry, I meant to say dt, not a t. Okay. So here we are. We could go ahead and we could do these two integrals. And if you do these integrals, what you'll find for this first integral, you end up with negative 18. For the second one, you end up with 14.66. Okay. So we take the absolute value of the first one, and we will end up with our total distance traveled is 32.66. And of course, this 6 here just repeats endlessly. Okay. So if we didn't take the absolute value here and we added them, we would get the 10/3 that we had before. So we just need to switch this area over to a positive area. Okay. Let's take a look at. So I got one more example here, I think, involving position, velocity, and acceleration. We can take a look at this here. So example 2 here. The acceleration function of a moving particle is, a is a function of t equals -4, and they tell us that the initial velocity is 12, and that t goes from 0 to 8. So they're basically telling us v at 0 equals 12. Find the velocity function and the distance traveled from t equals 0 to t equals 8. Okay. So they're giving us the acceleration function. They ask us to find the velocity function. So how are we going to find our velocity function here? What do you think we have to do? How are velocity and acceleration related in calculus terms? What do you think, Lee? So if we want to find velocity, what do we have to do to acceleration? Yeah. Basically, we want to do the indefinite integral here of our acceleration function. So if we take, let's just sub this in here. So we want to do I should have a dt in there, sorry. So we want to do the indefinite integral of -4 dt. So basically we want the antiderivative here, which is going to be -4t. And because we're doing an indefinite integral, we have to add on our constant of integration c, because we don't know, again, because it's an indefinite integral. If we want to find the exact velocity function, we need to figure out what that constant of integration is. How are we going to do that? Go ahead, Lee. Absolutely. We know our initial velocity, v at 0 equals 12. So we're going to sub in 0 for t, and that's going to tell us that c here is equal to 12, clearly. So we can get our specific velocity function in this case is -4t plus 12. Okay. What do they want us to do here? They want us to find the distance traveled from t equals 0 to t equals 8. Okay. So we first have to figure out, does this thing change sign over our interval 0 to 8? I'll say the closed interval 0 to 8. Okay. Question mark. And if so, where? Well, let's just set this equal to 0 and solve. 4t equals 12, t equals 3. So at t equals 3, this thing changes from positive to negative, or from negative to positive. Now, which one is it? Positive to negative? T3. That would make sense. Hold on. So we've got two intervals here. Let's see. We've got the interval from 0 to 3. Okay. And then we've got the interval from 3 to 8. Okay. And on this interval from 0 to 3, we want the absolute value of v at t, because we want the distance traveled. It is going to be, it starts off being positive. So the absolute value is just going to be the original function, because we know it has positive values on that interval. So it's positive from 0 to 3. On the interval from 3 to 8, if we want the absolute value, we need to have the, well, we need to change this to the opposite. We want the negative of that function. Okay. So we can set up our integral here. It's going to be the integral from 0 to 8 of our absolute value of our velocity function. Okay? And as we did before, we're breaking this into two intervals. We're going to have the interval from 0 to 3. On that interval, the absolute value of our velocity function is negative 4t plus 12. And then we're going to have the integral from 3 to 8. On that interval, we again want the absolute value of our velocity function, which is going to be 4t minus 12. Okay. Basically, we have to change the sign in that of the velocity function. And then we can do our integrals here. This integral evaluates to 18. Our second integral evaluates to 50. So we end up with 68 here. So we should say that the distance traveled, well, is 68 meters.